In this video, we're going to be focusing on complete solutions. So we're actually going to use the exact same note sheet and the exact same problems from yesterday, 8.6 day 1, but we're going to add the complete solutions to each of these problems. So with complete solutions, it's just like what it sounds like. They are complete. Whereas with restricted domain solutions, we were restricted. So think of complete solutions as any possible value of x that would satisfy these equations. Now, it would be very annoying and tedious to write out every single possible answer because there could be infinite amount of answers, I should say. So I'm going to show you what this looks like to represent all of the complete solutions that we have. But before we jump into a problem, I want to look at the unit circle here. And let's look at pi over 3, for example. So if pi over 3 was one of our solutions, we have to remember that we can continue to rotate around the circle and get more solutions. So when we say pi over 3 is a solution, think of it as the position of where it is on the unit circle. Because if I take one rotation around the whole unit circle and I land back at pi over 3, well, it's not actually pi over 3 anymore. Think about what did we add when we went an entire rotation around the unit circle. We added 2 pi because an entire rotation around the unit circle is 2 pi. Well, what if I went around the circle again and I still landed back at that position of pi over 3, but knowing we went around the circle twice? So I would have to take 2 pi and essentially multiply it by 2 to signify that I went 2 rotations around the unit circle. If we went around again, that would be 3 rotations around the unit circle. So I'd have to multiply the rotation of 2 pi times 3. Obviously, this could keep going and going and going. We could multiply by 5 to indicate 5 rotations around the unit circle. We could multiply by 100 to indicate 100 rotations around the unit circle. So instead of listing out every single number of rotations that we could do, we just simply use the variable k, and k represents the number of rotations that we would go around, and we know that that's an infinite number. So when you have a solution of pi over 3, and we're talking about complete solutions, any number of rotations around the unit circle constantly would give us another value and another value and another value. So a complete solution would look something like this. Now, if we have more than one solution, we might have multiple values from the unit circle listed in our solutions. Now, what if we have pi over 3 as one of our solutions and 4 pi over 3 as one of our solutions? Well, we could say, okay, pi over 3, and then we could do multiple rotations around the unit circle and continue to get more values. We could do the same thing for 4 pi over 3. So now 4 pi over 3 would be one of our values, and every time we add 2 pi, we'd be getting another value that would satisfy the equation. So again, we could say, all right, well, we'll multiply 2 pi by k, and k represents any number of rotations that we take from the position of 4 pi over 3. Now, while that's still technically correct, we can think about a shortcut or a more efficient way to write our complete solution in this situation. So what I want you to notice is that pi over 3 and 4 pi over 3 are diagonally across from each other on the unit circle. So essentially, in order to get from pi over 3 to 4 pi over 3, that is a semicircle. That's half of your circle, which would be pi. So we know that a full rotation around the unit circle is 2 pi. So half of the unit circle would just be pi. So a shortcut that we can do is we can say pi over 3 plus pi will take us from the position of pi over 3 all the way to the position of 4 pi over 3. So that's a more efficient way of listing these answers. And since this rotation can continue going around, if I would add pi again, then I would be going back to the position of pi over 3 on the unit circle. So that can keep going. So we'll still use k to indicate that this is any number of rotations. So let's go back to our problems from yesterday's notes. We already know what our x values are that satisfy this equation, and we already know what our restricted domain was. So what we really want to look at here is what our original solutions were before we looked at any restrictions, and that was pi over 3 and 5 pi over 3. So what I want you to notice is that those two values are not diagonally across from each other on the unit circle. That's your big hint. So for your complete solution, you're going to be adding 2 pi k to each of those values, and that represents all the rotations, all the possible solutions for this equation. Here's number 2. So because we're talking about complete solutions, we're not worried at all about the restrictions. So we want to look at what our original x values were before any restrictions. And the big thing that you want to notice is that those values are not diagonally across from each other on the unit circle. So for your complete solution, you're going to have both of those values with a plus 2 pi k. Now, number 3 is a really good one to look at. So without any restrictions, our x values, we had 4 of them. Now, here is one way to represent your complete solution. You have each of your x values plus 2 pi k. Not technically wrong, but there is an efficient shortcut that we can use because pi over 3 and 4 pi over 3 are diagonally across from each other on the unit circle. So because of that, we can say pi over 3 plus pi k. Similar with 2 pi over 3 and 5 pi over 3. They are diagonally across from each other on the unit circle. So we can just say 2 pi over 3 plus pi k. So as you're doing these problems, we do want to get into the habit of being efficient and using that pi over k. For number 4, we had a few x values. And on our unit circle, pi over 2 and 3 pi over 2 are directly diagonally across from each other on the unit circle. So we can use pi over 2 plus pi k. And then 4 pi over 3 and 5 pi over 3, they are not diagonally across from each other. So we're going to have 4 pi over 3 plus 2 pi k and 5 pi over 3 plus 2 pi k. And number 5, we had a handful of x values for this problem as well. So when we look at where they're at on the unit circle, 0, which is also the same as 2 pi as far as position goes, and pi are directly across from each other on the unit circle. So all we need to do is 0 plus pi k, and that will hit both of those positions. And we also have pi over 4 and 5 pi over 4 directly across from each other on the unit circle. So we can say pi over 4 plus pi k.